Okay, so let's talk about some factoids here, okay? Some of these things are useful to know, but when it's something I say you need to know, you must know, I'll make sure I point that out, okay? These things, they're useful to know, but I'm not going to require, unless it appears in a later slide, that you need to know. Okay, so gasoline delivers about 15 times the energy of an equal weight of TNT. It's not so surprising, I guess, that gasoline has more, but 15 times, that's huge. Coal is 20 times cheaper than gasoline for the same amount of energy. This is why people are, one of the reasons people are interested in coal. There's lots of it, particularly in the US and Australia, and it's cheap. This one you're going to need to know, okay? We'll talk about it later, and at that time I'll say you need to know this, but I'm just going to give you a heads up. You need to know this. There's several things with the solar that it's useful to know the numbers. 1 square mile of sunlight at midday could provide 1 gigawatt of electric power, which is the same as a large coal or nuclear power plant. So if you have 1 square mile, hunk of land, 1 mile by 1 mile, okay? By 1 mile by 1 mile. At midday, now, a difference is sun isn't always shining and it's not midday all day, etc. But at midday, it provides the same amount of power as a large coal or nuclear power plant. That's pretty amazing. Gasoline has 1,000 times as much energy as an equal weight of a flashlight battery, and 100 times as much as an equal weight of computer batteries. Computer batteries have a much higher energy density than ordinary flashlight batteries. But gasoline is huge. So liquid hydrogen has 4.5 times less energy per gallon, per volume, you see, than gasoline. And we'll revisit this in a few minutes. 4.5 times less per gallon than gasoline. That's liquid hydrogen, okay? That's kind of surprising. I always think about hydrogen being so explosive and everything, but once again, gasoline is big time. Energy from non-rechargeable batteries costs 10,000 times as much as electricity from the wall. Wow, this is enormous. 10,000 times as much. Amazing. Okay, so here's some more comparisons. For the same weight, see, this is where things get tricky. Sometimes and it depends what point you're trying to make. This is important for educating your policymaker. When it's advantageous to you, you'll compare things by weight, or if it's more advantageous to you, you'll compare by volume. Okay? You got to keep this in mind. Are we talking comparison by volume or by weight? They're not the same thing, right? Unless everything had the same density, which they don't. So, for the same weight, gasoline delivers twice the energy of coal, twice the energy of methanol. Now this is an interesting one, right? This was from the quiz. We talked about volume before, sorry. But the density is very similar there, so. Okay, twice the energy of methanol, which is wood alcohol, 1.5 times the energy of ethanol, and 1.1 times the energy of butanol. Butanol is, it's an alcohol that's related to butane, okay? And it's an important possible biofuel. It's kind of easier to make butanol from bio stuff that you don't eat than it is to make alcohol from bio stuff that you don't eat. It's ethyl alcohol, for example. Okay, so I have a note there about this alcohol. So gasohol seems cheaper than gasoline. See, gasoline has more energy than ethanol, and if you go to the pump, gasohol is cheaper than gasoline. If you go to you have choices when you buy your fuel, and if you buy the fuel that has more ethanol in it, it's cheaper per gallon. And so it looks like, yes, this is what I need to do. But because the energy content is so different between gasoline and ethanol, which is the additive of gasohol, per mile, the more energy it has per gallon, the farther you're going to go. So per mile, gasohol is actually more expensive than gasoline. So this is something to keep in mind. So what is better than gasoline? So what does beat gasoline in energy per weight? Well, natural gas by weight is 1.3 times better. Remember we said that hydrogen gas or liquid was worse than gasoline? That was by volume, okay? But if you go by weight, liquid or it doesn't matter if it's liquid or gaseous then, I mean, it just takes more of it to have the same weight as the liquid. So hydrogen gas or liquids has 2.6 times the energy content of the equal weight of gasoline. Okay, so once again, I want to emphasize the difference between comparing things by weight and comparing things by volume. When we get to specific cases, we'll bring this up again. Uranium or plutonium fission is 2 million times more energy content per weight than gasoline, and hydrogen fusion is 6 million times better, and matter, antimatter combining like in the Starship Enterprise is 2 billion times more energy per pound. Okay, don't think we're talking about running my car on antimatter or fusion or fission, but fission and fusion, fission for sure, we do use for energy production. Many countries do. And fusion, maybe someday people will use for commercial energy production. Gosh, these crazy symbols never come up. All right, now, they do on my computer. I have to talk to Peter about this machine here. So, these are useful equivalents, and I'm not saying you got to memorize these, but we'll see them again and again. And some of them I will tell you to memorize. But for the purposes of this class, and I said it before, a horsepower is the same as a kilowatt. They're both units of power, and they're essentially the same. Actually, a horsepower is only about 3/4 of a watt, which means that, 3/4 of a kilowatt, sorry. And so, it's not an exact. But for the purposes of this class, that's good enough. And it's really useful to make ballpark estimates on the fly using this kind of equivalency. If you want to get the exact number, you can always look it up. For the purposes of this class, this is the number we use. This is the equivalency we use, and it's not going to change anybody's arguments that we're using this instead of that. Okay? And it's much easier to remember. Typical home consumes about 1 kilowatt of power. Okay? And remember the difference between energy and power. Okay? Don't say 1 kilowatt per hour. No. It's 1 kilowatt. That's the power consumption. If you want to talk about the energy consumption, you take your power consumption and multiply it by time. Like an hour, for example. So, for example, in 24 hours, an average household uses 24 kilowatt hours, because you're going to take 24 hours times 1 kilowatt for the typical home. That's going to be 24 kilowatt hours. You just multiply them together, that gives you your energy. And your energy bill is in kilowatt hours. They charge you for energy, not power, which makes sense. Average cost of electrical energy in the U.S., averaged over all the U.S., is about 10 cents per kilowatt hour. Here in Manhattan, I think it's a kind of a funny thing. For a little amount, they charge you this. The next amount that you use, they charge you a different rate, etc. But it's ballpark, I think, about 11 cents per kilowatt hour here in Manhattan. But averaged over the whole U.S., about 10 cents per kilowatt hour. And 1 kilowatt hour is approximately equal to 1,000 food calories. We eat about, this is all about, we eat about 2,000 food calories a day. And that means that's the electrical equivalent of about 20 cents a day, right? If you say that a kilowatt hour is 10 cents, and a kilowatt hour is about 1,000 food calories, and we eat about 2,000 food calories, that means it's like 20 cents worth of food in terms of its energy content. If we were able to consume electricity, we as people were able to consume electricity instead of food, then it would only cost us about 20 cents a day, which is about $73 a year. Now, I don't know anybody in the U.S. who's able to feed him or herself on $73 a year. Okay? So our food is much, much more expensive. Our homes are expensive. For our homes, taking the same number, right? Average home is 24 kilowatt hours. And 1 kilowatt hour is 1,000 food calories, so that's like 24,000 food calories, whatever. Or you can turn it into money. You could say 24 kilowatt hours, 10 cents per kilowatt hour makes 24 times 10 cents, which is $2.40 every day, every 24 hours, $2.40. I want you to look at these numbers, and given that this just means approximately, okay, I want you to see if you can reproduce these numbers here, this number, this number, this number, this number, and this number. Well, this is nothing. This number, this number, this number, this number. See if you can come up with those numbers given these facts. Okay, you need to be comfortable doing that. If you want to make comparisons, oh, you know, I need to build a power plant here in Manhattan, Kansas. I'm going to give advice to the city commission of whether they should do that or not. And then I'm going to say, well, okay, I can look up, I can get a bid for how much it'll cost me to build this thing, but I need to know how much it's going to cost. I need to know how big it needs to be. I need to know how many homes do we have in Manhattan, Kansas. You can estimate that. Then you can say, well, if it's a typical home, okay, and this is how much it's going to cost then. Now we know how much money we're going to have coming in to pay for the power plant. These are all calculations you should be able to make, because we're not talking rocket science here. We're talking just using these very simple numbers, not simple concepts, but simple numbers to try to come up with something really practical. Okay, you don't need to be an engineer for this. You just look at the bottom lines here. All right, so see if you can come up with these numbers and see why these are the right numbers given this stuff here. Okay? It's not an assignment, it's just good advice.